All right, so now we're ready to begin discussing how to calculate your equilibrium expressions using partial pressures. So far, we've used concentration to define our equilibrium constant, okay? So if we were to look at this reaction, right, where we had 2SO2 plus O2 in equilibrium with 2SO3, we could write our equilibrium constant in terms of concentration, and we would have a Kc for concentration, which was equal to the concentration of our products over reactants, right, where we had the concentration of SO3 to its stoichiometric coefficient of 2, all over SO2 raised to 2 times the concentration of O2 to the first power, which was its stoichiometric coefficient, okay? Now, if we're looking at all gases, okay, then we can use our partial pressures, right, our PIs, right, that we talked about at the beginning of the semester. Now, in this case, our Kp, our equilibrium constant using pressure, is equal to the partial pressure of our products over reactants. So rather than using our concentrations, we just use the partial pressures. So it's exactly the same, except we have partial pressure. So we would take the partial pressure of SO3, raise it to its stoichiometric coefficient of 2. Then we would put that over our reactants, right? And our first reactant is SO2. So we have our partial pressure of SO2 raised to the second. And we have our partial pressure of O2 raised to the first, using, again, those stoichiometric coefficients. Now, if we calculate our Kc and our Kp, they're, in general, not going to be the same number, okay? Now, Kc can be converted to Kp by using this equation here, which says that Kp is equal to Kc times the quantity of RT raised to the delta N, where R is our gas constant, T is our temperature, and delta N is our sum of the stoichiometric coefficients of our products minus the sum of our stoichiometric coefficients of our reactants, okay? Now, I defined our gas constant here, if you've forgotten. So R is equal to 0.0821 liters atmospheres divided by moles Kelvin, okay? Now, since we're dealing with Kelvin, remember to convert your temperature to Kelvin as well. Now, to give you an example of how the delta N calculation works, I figured we would start with a quick example, all right? So if we had this reaction where we have AA plus BB plus, or is in equilibrium with CC plus DD, okay? The little letters, as always, are going to be our stoichiometric coefficients, okay? So we're going to take the sum of our stoichiometric coefficients for the products minus the sum of our stoichiometric coefficients for the reactants, okay? So I'm going to take the sum of my products, which is C plus little d, right? So this is my sum of n products, okay? And then I'm going to subtract off the sum for my reaction, or the sum for my reactant coefficients. So I've got A and B. That would be the sum of n reactants. Okay? That's all you got to do to get your delta N. Okay? Now, to walk you through, I know you guys like to have numbers. That was another comment that you guys sent out, so I want to make sure that we're doing that for you. Okay? So, we can move on to slide 12. There's an example of a problem on slide 12. Okay, and it says that at 1,000 Kelvin, okay, that's a little wonky. At 1,000 Kelvin, or sorry, not 1,000, at 1,100 Kelvin, right, the Kp is equal to 0.25 for the reaction of, I'm going to fix that. Okay, for the reaction given by 2SO2 plus O2 in equilibrium with 2SO3. Okay, so it's again that same reaction that we were just looking at. Okay, now what they want us to calculate is what is the Kc that temperature. All right, so our first step when we have any problem like this, right, is if it's asking us to convert to Kc and we have Kp or vice versa, we're always going to write down our Kp-Kc equation. Okay, so the first thing that we do is we write down Kp is equal to Kc times the quantity RT to the delta N. Okay, now what do we know? Well, R is a constant, we know that. We know our temperature is 1100 Kelvin. Now, I want to make sure that my R and my Kelvin, or sorry, my R and my T have the same units. So if this R is in Kelvin, then I want my temperature to be in Kelvin. So if I gave you one in Celsius or Fahrenheit, you'd need to convert to Kelvin. Okay? Now, we have our temperature in Kelvin. Good. And we also have our Kp. So what don't we have? Well, it's asking us for Kc, so we don't have that. And another thing that we don't have is we don't have our delta N. All right? So the next thing, we're going to calculate our delta N. All right? Now, how do we calculate delta N? Well, we know that delta N is going to equal the sum of our stoichiometric coefficients for the products minus those of the reactants. Okay? Now, looking at this reaction, right? What is our sum of stoichiometric coefficients for the products? Well, we only have one product, and that's our stoichiometric coefficient. So it must be a 2, right? There are no other products, so that's the total sum. And then I'm going to subtract off the sum of the stoichiometric coefficients for the reactants. Okay? So I have 2 SO2, so I'm going to do 2, and then I also have 1 oxygen. So I'm going to also add that, because again, you're adding all the coefficients for the reactants, okay? And you're subtracting all of that away from the sum for the products. So you take the sum of the products minus the sum of the reactants, right? So from this, you get 2 minus 3, which is equal to a negative 1. All right? Now, let's solve this symbolically. For what we want, and in this case, it's Kc. Right, so Kc is equal to Kp divided by the quantity RT to the delta N, right? Then we're going to plug in all of our values, all right? So we have our Kp, right, which was in the problem statement at 0.25, all right? Remember that all of our constants are going to be dimensionless for equilibria. Now, and then we're going to divide that by our gas constant. So we have 0.0821 liters atmospheres per mole Kelvin. All right. And we are going to multiply that by the temperature of 1100 Kelvin. And then we're going to raise all of that to the delta N that we just calculated, which was a negative 1. Okay, now make sure that you put all of that into your calculator, and what you'll find is that Kc is in this case equal to 22.5665. Now what about sig figs? Well, the Kp was given in the problem statement, it only has 2 sig figs, so this will get us down to 23 as our equilibrium constant. Okay, so that would be how you do a calculation for your delta N, as well as how you can convert, as an example, between Kc and Kp. All right, should be pretty straightforward. Just a little bit of algebra. All right, now, so far, all of our equilibria have been in the gas phase, all right? Now, when all of the species are in the same phase, slide 13, when all species are in the same phase, and by phase I mean like solid, liquid, gas, okay? When they're all in the same one, okay? This is called homogeneous equilibria. Okay, so if they're all in the same phase, it's homogeneous equilibrium. Now, on the other hand, if reactants and products are not all in the same phase, this is called heterogeneous equilibria. All right? So if they're in the same phase, homogeneous. If they're not in the same phase, it's heterogeneous. All right? Now, for example, we could have something like calcium carbonate, so CaCO3 solid, and that could be in equilibrium with calcium oxide solid and carbon dioxide gas. Okay, now how do we write our equilibrium constant for this reaction? Well, we could think of it like this, right? We would have our K, and if we did this in terms of concentrations, we would initially think that maybe our Kc would be equal to the concentration of CaOS to the first times our concentration of CO2 gas to the first all over our concentration of CaCO3 solid, okay? But as it turns out, okay, if they're not all in the same phase, the phase that has the most disorder is going to be the one that dominates, okay? So what I mean by that is, if we have a gas, gas always wins. So we're going to not include the solids, okay? So I have our concentration of CO2 gas to the first, that's my equilibrium constant. So if I have gases in any other phase, gases always win. If I have liquids and solids, then the liquids win. And if I have all solids, then I would write it as all solids. Okay? So, gases greater than liquids greater than solids. Okay? So if you have one gas and the rest are other phases, the gases are going to win. Okay? If you have liquids and solids, the liquids are going to win. Okay? And so on. All right? Now, that's that. So, again, notice that we had solids and gases in this one, so our equilibrium constant was much simpler. All right? So, keep in mind that solids and liquids will not appear if we have gases. Okay? In our Kc for equilibrium. All right? Now, so now that we have defined K, how does it affect our reactions? All right, well, for this, let's move on to slide 14. Okay, now on slide 14, this is where we talk about understanding our K, right? our equilibrium constant. Now, in order to do that, let's consider our reaction coordinate, right? Remember that thing that we talked about at the end of the last chapter, right? Where we started with our reactants, we went up, and then we went down to products, right? On this side, right, we have reactants. On this side, we have products. Okay? We had an activation energy, right? That was our EA, or our activation energy. And remember that our activation energy was that energy required to go over that hump. Okay? The activation energy says that the reaction rate depends on EA. Okay, right? Our rate depended on how high that hump was. Okay, which meant that this was important to kinetics. Right? That was our chapter 12 topic. Right? Now, in this chapter, we're talking about equilibria. Okay? We're talking a little bit about thermodynamics. Okay? Now, the difference between our reactants and our products, that's what's called delta E. Okay? Or our change in energy. Okay? Now, that delta E has a direct impact on the magnitude of our equilibrium constant. Okay? So, as delta E changes, so does our equilibrium constant. Okay? So, that's telling us a little bit about whether or not we favor the products or the reactants, right? Which is something that K directly tells us, okay? Now, the more stable, the greater our delta E, all right, the more likely a reaction will favor the products. If, on the other hand, right, if we had products that were high in energy, okay, then that would mean that our delta E was negative, or sorry, delta E was positive, right? Because we had to go over the hill, right? If we had something that looked like this, okay, where our delta E was positive, if delta E is positive, then that means that this reaction required energy, which means that it actually favors the reactants, okay, which tells us that as delta E changes, so does our favorability with K, all right? So that means that delta E is related to our stability and our equilibria, which means that it's related to the topics of chapter 13, okay, the one that we're talking about now. So again, the height of it affects the rate, which was kinetics, and then the difference between our product and reactant energies, that affects our equilibria, okay? Now, the next thing that I want to talk about is our reaction quotient, which is on slide 15. All right, now, since we were just saying that the change in energy, like our delta E, affects that magnitude of K, okay, that means that depending on how many products and reactants we have, right, we're not changing the energy. But if we have a bunch of products, right, like say we had a bunch of cars up here, right, they're going to want to spread themselves out into a better parking lot, right? Or if we had a bunch of students crammed in a room, right, they'd rather be spread out, right? So they would want to spread over that hill, right? And reform that equilibrium so that way everybody's more comfortable, right? So in this case, right, where we have our high energy state, okay, then it would be favorable where we have a bunch of cars to go back a little bit, right? So you can imagine that there's a push and pull, and we'll talk more about that later. But to introduce this idea of the reaction quotient, okay, we know that K, EQ, tells us or gives us information at equilibrium, okay? But if we're away from equilibrium, right, like say that we had that classroom, let's say we had 2 classrooms, right, and one had a bunch of students packed into it, right, and this one only had like 3, right, you could imagine that it wants to spread out, right, it wants to form equilibrium. So if you had a lot of reactants, okay, it may want to push toward the products to establish that equilibrium, right? So depending on where you are, right, KEQ tells you about the equilibrium, right? So KEQ is going to tell you, oh, okay, I've got 5 in each room now, right? I've established the equilibrium. They've sort of had a chance to spread out, okay? This one's at equilibrium, but this one isn't, right? So if we aren't at equilibrium yet, then we have to use what's called the reaction quotient. And we call that capital Q, okay? Now, this capital Q, this reaction quotient, happens to be very useful for telling us which way a reaction will shift. To reach equilibrium, right? In that case with the classroom, right, that had a bunch of students, they all wanted to shift to the right, yeah, so that it spread them all out. Okay, well, if we had a bunch over in the right-hand classroom, then they may want to shift a couple over to the left to establish equilibrium, okay? Just because of where you start with doesn't mean that it's going to, like, remember, it doesn't matter where you start with, they're all going to shift to equilibrium, okay? So if we have different initial conditions, right, everything's going to go to equilibrium if we have a competing reaction, okay? So our reaction quotient is just like, it's just like K, but not at equilibrium, okay? So, I know that was kind of a long-winded way of saying this, but let's say that we had the reaction N2 plus 3H2 in equilibrium with 2NH3, okay? If we have this, what would my KEQ be? Well, my KEQ, if they were all at equilibrium, is going to be defined as NH3 concentration, fix that, my NH3 concentration to its stoichiometric coefficient. Remember that when I first introduced it, I had my little EQs down here. Okay, those are going to be really important now. All right, and that was my product. And then I put that over my reactants. So I had my concentration of N2 raised to the first power at equilibrium. And then I had my concentration of H2, all right, at equilibrium raised to the third power. This is how we define our equilibrium constant, okay? Now, Q is just like our equilibrium constant, except that it's our initial concentrations. Okay, so here we have NH3, just like before, but it's our initial concentration, and we raise it to our stoichiometric coefficient. And then we have N2, our initial concentration, raised to its stoichiometric coefficient, times our H2 concentration initially. Those are little zeros, okay? I always put a line through my zeros to keep them separate from my O's. Okay, so I have my concentration of H2 initially raised to its stoichiometric coefficient, which was a 3. Okay, so again, this one's at equilibrium, and Q is your initial. All right. So I think this is probably a good place to stop. And then in the next video, I will go through a couple of examples because I feel like that would be good to kind of solidify this for you guys. All right.